This is the 8th installment of the Crash Course Regions Chemistry series, and this is going to be on the Redox unit as pertains by the New York State Regions curriculum. So I'm going to go over all the things you have to know for the redox portion of the test, or the questions that pertain to redox, oxidation, reduction on the New York State Regions. So let's get started. Okay, well, first and foremost, you have to understand some basic understandings of electrochemistry or redox. And first of all, let's start with oxidation. Okay, oxidation is an old word that came from the idea of what oxygen used to do to things. Now, we knew that oxygen in the presence of some metals, okay, made them rust. Okay, case in point, if the metal I'm talking about is iron, okay, we knew that if you had exposed iron, oxygen with the iron would make the rust or the iron oxide. Sometimes we'd call this an ore, an imperfect amount of metal. So iron oxide could look something like this. Could also look something like this. Okay, this is iron 2 oxide, this is iron 3 oxide for the naming principles we've done before. Now, this ore, and sometimes they'll use the word ore when we find these things in the ground, these ores, most of the time we find oxides of metals in the ground. We have a lot of bauxite, which is aluminum oxide, okay, which is this right here. So most countries have this aluminum oxide, this ore of aluminum. It's very, very cheap. Everyone has it. The process of purifying these metals into their pure states, okay, has to do with redox. Reduction oxidation reactions purify these metals. So a lot of these metals we find in the earth, with the exception of, let's say, the gold or the inactive chemicals, okay, are usually ores or oxides, which we call rusts of the compounds. These have reacted with the oxygen. And what's happened here? Well, the action of the oxygen has pulled the electrons from the metals. We should know enough that metals hold on to electrons loosely, and nonmetals like oxygen are small enough with a high electronegativity absorb them. So clearly, if I've got iron and I've got oxygen, okay, what's going to happen is the oxygen is going to yank the electrons away from the iron. It's going to make the iron oxidize. The process of the oxygen makes the iron oxidize. Okay, so that's where the oxidation came from. And the iron becomes charged. Let's say it's +2. The oxygen, or one of the oxygens, let's say, of the two, absorbs those 2 electrons and becomes -2, and what you make is that iron 2 oxide, as I just mentioned, and that's a form of ore, iron 2 oxide. Sorry, Roman numeral 2 to denote that the iron is +2, oxide because it's binary. Okay, and that is one reaction, and of course I don't have it balanced. Okay, so let's balance that, 2 here and a 2 here, and that would be a redox reaction because oxidation was occurring by the use of the oxygen. The oxygen was strong enough. Now, however, we figured out long ago that this ability to draw the electrons away from the metal, okay, makes this object oxidize, and we call this the oxidizing agent. We don't really use that much anymore, but the oxygen forced the iron to undergo this oxidation, which is the loss of electrons. Okay, so we use this mnemonic, Leo the lion says grr. Losing electrons is oxidation. So iron lost electrons. And what did it become? Well, it became iron oxide in this example I gave you, which is really +2. And we're going to separate that now. So iron becomes iron +2 by losing 2 electrons. So oxidation, okay, is the loss of electrons. And we have that mnemonic, Leo, the lion says grr. Now the grr part is gaining electrons. Now who gained electrons in my simple example? Well, the oxygen. One of these oxygens, which we're going to find out are electrically neutral, became O negative 2. And how that happened? By gaining 2 electrons. Notice we call this reduction. Now it's very strange for some people when you think about reduction, because how can I gain electrons and be called reduction? Well, this idea of reduction comes from the charge being reduced. We're starting with an element, and we should know elements, or this word that I've been talking about in my reviews, atom. Atom always means neutral. Why is it neutral? Because the protons equal the electrons if it's an atom. So it's always electrically neutral. Any standalone atom is electrically neutral. Now, if you're starting at a 0, or the charge of an atom, neutral, and you gain 2 electrons, your charge, or we say the oxidation number, goes down. That the number of oxidation, it all started with what oxygen did to other compounds. So reduction means that your charge went down. Essentially, we're going from 0 to negative 2. And how did our charge go down? Because we gained electrons. And you know why oxygen gained electrons. It's very electronegative. We've talked about this in the periodic table and the bonding unit. The metal started out as an atom as well in my simple reaction. And it's going from 0 to plus 2. It lost electrons and became positive. We know metals do that. We've talked about this in other crash courses. So this is kind of like a little bit of review. Redox is nothing more than a review of a little bit of atomic structure, absolutely, and ionic bonding, because we're talking about ions here. So look at this, Leo, oxidation, the number increases. Reduction, your oxidation number decreases. It's all about the electrons being passed around. So redox reactions are nothing more of the idea that we have redox means you have reduction, and the ox part means oxidation. And my friends in chemistry, it's about the passing of electrons. The one who oxidizes gives the one who reduces electrons. Oxidation is loss, Leo the lion. Reduction is gain, gaining electrons. So electrons will always flow from the one who loses to the one who gains. It doesn't make any sense otherwise. Okay? And all of these properties and things I'm talking about will come up in other parts of this unit that I'm going to review in its entirety. So those are the basics. We have someone losing, and you've got it. Metals tend to oxidize because they like to lose electrons. And you got it. Nonmetals, which are smaller, and they attract their electrons like OCD, like they're mine, gain electrons, hold on to them tightly. They tend to reduce. Now, it's reduction by gaining because their charge goes down. Metals' charges go up as they lose negatives. So it's about the electrons being passed around. And believe it or not, a Regents question pops up. You know, can you have reduction without oxidation? And of course you can't. You can't have someone losing unless someone's gaining in this case. So electrons are being passed around. Okay, very important. That's essentially the basics we have. Now, before we go further, now that we have some basics in understanding what's reduction and oxidation, we have to put this to practice and identify reactions that are, okay, redox reactions. So how do we identify a redox reaction, a reaction where electrons are being passed around? Well, there are many ways to do this, okay, but the first way is to notice, okay, that the oxidation numbers are changing. Okay, now what do I mean by that is if the oxidation numbers are changing, that means electrons are being passed around. Let's go back to this example right here. Okay, in fact, I want to rewrite it since it's a big mess that I've made. So I have the iron, 2 irons, plus the O2, making that one form of iron ore, or iron oxide, rust. Okay, and how do I identify this as a redox reaction? Well, the one way to notice is that the numbers will change. Now what numbers? The individual numbers. Now we're starting with an element. We should know that elements always are electrically neutral. This one is also electrically neutral. And if it's bonded, if atoms are bonded to something, they're going to have oxidation numbers other than 0. We know oxygen is -2, oxidation state, so this iron has to be +2 because all compounds are going to be electrically neutral. So what we do is we assign oxidation states. So the first thing to understand is you're going to assign oxidation states or oxidation numbers. They're easy if they're atoms in their elemental state, whether they're bonded to themselves or just hanging out. They are 0. The protons equal the electrons. But if they're bonded to something, they have something other than 0. So to identify a redox reaction, and this works about 98% of the time, okay, all you have to do is find one atom or one element hanging out in the reaction, and you know it's a redox reaction. And why does this work? Because if you can find one neutral atom, go find that 0, you know that it's something other than 0 on the other side, which means the oxidation numbers are changing. And why are they changing? They change because electrons are either being lost in oxidation or gained in reduction. Let's go to table I and let me show you what I'm talking about. So when they ever ask you for what type of reaction is this on a part 2, a lot of times, and of course there are some exceptions, it's a redox reaction. Let's go to table I and let me show you what I'm talking about. So table I lists a bunch of reactions with their enthalpies, their delta H's, their heat of reactions, exo or endo, but I'm not really worried about that. I'm trying to look at these reactions. These are combustion reactions, these first 6 here. Okay, or in this case first 7. And combustion reactions are denoted by this oxygen with this organic fuel giving me CO2 and water and very exothermic. So you can call this combustion, and this is the type of organic reaction you're responsible for. But if we look closely, can you find me a 0? And what I mean by that is, can you find me an element? And there it is, oxygen. Whether it's bonded to itself or not, is electrically neutral. Protons equal electrons. That's a redox reaction. Once you find just one, you know you have a redox. This is combustion, but it's also a redox reaction. Why? It's a 0 here. When it's bonded to something, it's something other than 0, which you'll find out to be -2. Its charges are changing. So all of these are redox reactions. So combustion is an example of a redox reaction. Now these reactions you learn are synthesis reactions or formation reactions. But aren't they also redox reactions? Can you find me an element? Of course you can. These are all elemental forms. Protons equal the electrons. So if you find 1, 0 anywhere in the reaction, it's a redox reaction. Now, why does it work? It works because if it's a 0 here, it's something other than 0 in here. The oxidation numbers are changing. Electrons are being lost. That's oxidation. Electrons are being absorbed or taken in. That's reduction because your charge is dropping. So that's how you identify them. So you can see that most of these reactions, you can name them redox. So if you had to name something and you forget it and you see a 0 or a standalone element, you know it's a redox reaction. Now, not all reactions are redox. These are ionic reactions. Okay, now why aren't these redox reactions? Well, if you look carefully in potassium nitrate, okay, we know from table E, a nitrate ion collectively, this polyatomic ion, is -1. And we know that K likes to become +1. And, well, K is +1 here, and this whole nitrate's -1. The charges are not changing. So this is not a redox reaction. So these ionic reactions, or all of these ionization reactions, although they are ionic reactions, they are all non-redox reactions because the charges are not changing. All you have is a positive attracting a negative, and they're separating. Also, double replacement reactions are also not redox reactions. Case in point, if I got lead nitrate and potassium iodide, which is the that yellow precipitate we make from 2 clear solutions, that demonstration you did or your teacher probably did, we know that lead Has to be +2 in this case because each nitrate's -1. We know potassium is +1, it's a group 1 ion, and halogens are -1. So when you split the positives and negatives and do a double replacement, all you're going to do is switch partners. So this lead +2 goes with the iodide, or iodine, and Pb is still +2. Iodine is still -1. That's why you need 2 of these. And when you switch partners, you realize that, hey, K is still +1, nitrate's still -1, so you need a 1-to-1 ratio. And you didn't change any charges, so double replacement reactions are not redox reactions. Okay, because their charges do not change. Now you should know that a neutralization reaction is really a double replacement reaction. For instance, 5-hydrochloric acid plus, that's an acid. Here's our base. It's a neutralization reaction. It breaks apart into the salt and the water. Okay, you should realize that this is really a double replacement reaction. Here's a negative. Here's the positive H. Here's a -1 for the chlorine, the +1 for the sodium, -1 for the hydroxide, and guess what? This +1 hooked up with this -1, and they still retaining their charges, and this positive hooks up with this negative. Nobody lost their charges. So these are not redox reactions, but they're easy to identify. Do you see any standalone elements? No, you don't. Here's a classic redox reaction called a single replacement. What if I had tin and copper chloride? Okay, what's going to happen is the tin's going to replace the copper and make tin chloride plus the free copper. This is a single replacement. Is this a redox? And you would say, yes, you see a standalone element. If it's by itself, it's 0. When it's bonded to something, it's other than 0. So that's very important you recognize. Now, however, we need to be able to write the oxidation numbers for these elements to know how much electrons are lost or gained. So one of the important skills of redox is assigning oxidation numbers, and let's go work on that right now. Okay, so the first thing that I'm going to do is understand that this compound is going to be electrically neutral. So the bottom number is 0. Now, what I'm going to do is find the individual charges, and hopefully they all equal up. Their individual ions collectively from everybody equals 0. So I must be able to assign oxidation numbers for many different questions that pop up. Not a difficult skill, but the first thing is to understand that the whole thing has to be 0, unless it's a polyatomic ion itself, and I'll go over that example. So first and foremost, I got tin chloride. I got a metal and a non-metal. So let's go look at the tin and the chlorine. So what I'm trying to do is try to find the oxidation state of tin. If you notice in the upper right hand corner, they tell you the charges the atoms love to become. So my problem here is tin has 2 choices. So I say, oh my gosh, so I can't start with the tin, right? The whole idea behind this is I need to know what the charges of the tin are in the compound so I can figure out in my reaction who exactly is gaining electron and who is losing. Besides the fact we're trying to identify which compounds or which reactions are redox or not, we're going to eventually want to know who exactly got reduced, who exactly got oxidized. We do that by figuring out what the charges have become or what are they moving to. So we have to be able to figure out the charges. But tin's got 2 choices. So that's tough. You can't start there. So we go to the chlorine, the non-metal. You may say, Mr. Grodsky, whoa, we got another problem. Chlorine's got a bunch of different choices. However, if it's a metal and a non-metal, right, it's tin chloride. This is the non-metal side. It's got to be what charge? If tin is positive and only can be positive as metals can only be, this has to be negative. So even though it's got multiple choices, it's only got one negative choice. So chlorine is -1. That's our starting point. So chlorine is -1. Individually, so I do the individual up top. Okay, the bottom is the overall. Now there's 2 of them. 2 times -1 is -2 overall. What must be the positive charge overall? Yeah, it needs to be 0, so +2. And since there's only one tin, it's +2 individually. So this is tin Roman numeral 2 chloride. Okay? Now, and that's how we do it.